Hi, this is Jesse Hoffman. I'm an electrical engineer with Energy Systems Group, and today we're going to look at protective relay CT saturation in a generator protective relay. This is for one of our generation plants at ESG. ESG is a energy services company who specializes in alternative energy, energy conservation, and distributed energy projects. So today we're going to look at one of our small distributed energy projects, and we're going to use this as a case study for evaluating CT saturation. The goals for this presentation are to get an understanding of a small distributed energy project and the configurations that are typical, and look at the equipment that we use and what challenges that it poses. We're going to become familiar with ETAP's CT saturation calculation capabilities. And we're going to walk you through that particular calculation. Then we're going to compare the results of the ETAP calculations to standard transient analysis programs, EMTP-RV and ATP-EMTP. We're going to take a look at those results and see if it's worth going the extra mile using the more complicated software programs. So in our situation, we are looking at a typical system. Our typical generation of projects include synchronous generators connecting at medium voltage. And they're going to connect to the distribution system using metal-clad switchgear or metal-enclosed switchgear, which we're seeing right here, and protective relays that are microprocessor-based type. These systems usually will connect to a medium voltage power grid of the utility or the customer site, and they're going to offset power purchased by the customer. So normally what they're going to do is run in grid parallel mode. They also have the ability to run in island mode, where it's just the generator powering up the power system and energizing the client loads without any utility. So what are the challenges here? So in our case, we're connecting to the distribution system at medium voltage, just like a normal utility substation would. So the utility short circuit contributions are relatively high sometimes, and just as high as they would be in a normal utility substation. So these high fault currents can lead to CT saturation during fault conditions. We are normally going to use all the same types of protection functions that would be seen in a utility substation, including differential protection, overcurrent protection, directional overcurrent protection. So a lot of times we're looking for some high-speed tripping applications. So we do get concerned about CT saturation and the potential for the protective relays to have an increased tripping time due to that saturation. So in our case, we're a lot like all of the other utility substations out there. Our projects kind of have all the same attributes. But one of the big problems that we run into a lot in our case is we just do not have the space to put in high accuracy CTs within our metal clad switchgear. So in that, what I'm getting at there is that in this overhead distribution system here with the outdoor substation, you have plenty of space to mount high accuracy CTs on the bushings that are seen in this picture right here. The manufacturer can design the bushings to accept a much larger CT, so they can accept the high accuracy CTs outside. There's a lot of space. So our problem is that within the medium voltage equipment, the metal clad switchgear here, there's limited space. It's a very compact design. So what you're looking at inside of this breaker cubicle right here is there's the stabs for each of the three phases of the medium voltage breaker. And then this square red portion right here is the actual CTs that mount on the breaker stab. So you can tell right away that there's going to be limited space within this enclosure for mounting CTs. And the problem that you have is that the high accuracy CTs are physically larger. So they're just on this bushing here alone, there just isn't enough space to mount a very high accuracy CT. In fact, what you can normally get away with is 2 low accuracy class CTs on each breaker stab, or 1 higher accuracy CT, but you can't usually fit the highest accuracy that would normally be available in an outdoor application like this. So you're going to look at a manufacturer's table, which we have shown right here, that indicates what you're normally going to be able to provide or normally be able to obtain from a manufacturer. If you're going to design this particular system, you're going to end up getting the standard accuracy class, which you can see here. The CTs that are of a low ratio have a very low C class accuracy. You have the option to additionally specify high accuracy class CTs, but like I said, you could get 2 of these on a breaker stab, but only 1 of these. As the current transformer ratio increases, the available accuracy class goes up. So at your higher CT ratios, you can get some relatively high accuracy classes here. But on all your lower ones, you're going to end up with a lower accuracy class, even if you're going with the higher accuracy CT option. So ultimately, that becomes a driving factor. And why is that a factor? Well, because we have a small distributed generation system that has low full load amps. So in our small generators that connect to medium voltage, we need to set our protective relays in a way that coordinates with the rest of the system. So in ETAP, you can pull up your protective relay, which we have shown right here, and you can see that the protective relay has a minimum setting of 0.5 secondary amps. So if we were to go with a very high accuracy, the highest accuracy class CT you could possibly get from this vendor, you would have a potential to not set that protective relay low enough to protect the equipment or to coordinate with other devices in the system. And that becomes really what the problem is, that the lower current transformer ratios have a lower C class and they have a higher saturation potential. And what that can lead to is misoperation of the protective relays. So that's what we're going to study in this particular case study. So in this system here, we've got a less than 3 megawatt generator. We're setting up the protection scheme like a traditional generator would with differential protection. We have 1 CT that is on the neutral side of the generator, and we have our utility side CT up here. And then what we have to look at is 2 different fault current scenarios. One is for the internal fault where we have fault current flowing from the utility to the fault. And you can see here that the utility fault current is quite high in comparison to the generator contribution, which is much lower. So what we're going to want to do is to evaluate both of these conditions, the high fault current and the low fault current situation, to see if we're going to anticipate having any relay misoperation. So for that, we've got our 305 CTs that we have here, and we got the higher accuracy version of that from the manufacturer, which is a C100. Of particular importance to this study, you need the excitation curve for the CT, and for the ETAP version, you need to know the secondary resistance. So you're going to have to get that data from the vendor of the switchgear for your particular CT application and accuracy class. So now let's take a look at the steps we need to do the ETAP evaluation. So the first step, of course, is going to be to watch the webinar. ETAP has a webinar that they have recorded that shows you step by step how to operate this calculation within ETAP. So highly recommend doing that. We're going to walk through that here in a few seconds. The next thing you have to do is gather the CT data, which I just showed on the last screen. And then, of course, you're going to need the burden information. And by that, we mean the wiring resistance and the burden of the protective relay. Then you have to perform a short circuit analysis using the STAR module in order to do this calculation. And then we get into the calculation itself. So let's take a look at ETAP and how to do this calculation. So the first step is going to be to click on the CT, double clicking on it. We navigate over to the rating page and we click the CT sizing button, which will bring up this calculation mode. So in this calculation, all we need to do is select the class, which we have our C100 class selected here. The ratio is auto-populated. The other thing that you need to put in, though, is the secondary resistance. So this value down here needs to match the data sheet for the CT. Then, of course, we have to do the lead resistance calculation by looking up the type of wire that's going to be in the switchgear and its total length to get our total burden of the wires connecting the CT to the protective relay. At this point, we could click over to see the saturation curve and characteristics on here, but first we need to put in our fault currents. So up here, if you're doing the star calculation first, it is going to auto-populate for you what it calculated for the amps and the X/R ratio. And you can also use user-defined values, which I have in here for the sake of this presentation. 1,000 amps coming from the generator. And then what we're going to do is put in our relay burden, which is right here. So as you can see, there is no warnings and no saturation noticeable on this for the low fault current case. So at the end of the day, that's a very easy process. It only takes a little bit of time. Most of the time you're going to spend doing this calculation is going to be probably obtaining the data to perform the calculation itself. So what did we find from ETAP there? On our screen, we can see that there was no saturation for the low fault current case, where the generator was the only supplying the current. And ETAP didn't indicate any warnings in that case, and the value of the RMS current that ETAP has calculated is greater than the pickup set point, so everything is going to be okay from that standpoint. So for our next CT, we're going to look at our highest fault current case, which was the 14,000 amps provided from the utility. So in ETAP's model, it's very simple to change this using the same CT calculation we just looked at. All the information for burdens and things can remain the same, and you just select the higher fault current case in the star module. So once we do that, ETAP is going to pop up with a warning here indicating that we need to reduce the burden of the CT sensing circuit, which in this case is almost impossible because the lead length from the CTs to the protective relays is very small, and most of the resistance in the circuit is the CT itself. So then what we're going to find over on the screen, which indicates the saturation results, is that the CT has achieved a pretty high level of saturation here, and the black line indicates the calculated saturated current, where the blue lines are indicating the ideal current. And the area of concern for us here is that the RMS current that the relay is seeing is just a little bit above what we anticipate our protective relay would be set at. So if this current were to drop off due to saturation and go below our pickup setting, the relay may drop out of pickup and then come back into pickup over here later in the curve and restart its timing out process. So essentially what that's going to do is delay the tripping time of the breaker. So when we see that the saturated current waveform isn't, pretty good above the anticipated set point, then that's when we're going to start wondering what we should do next. So what we wanted to do in this case is to verify the results. It looks like the results are very good, but very close to having a problem with tripping of the relay in the time that we prescribed. So the next thing we're going to do is check the results of ETAP versus some transient analysis programs that use the more traditional method of calculating the CT saturation. So for the first software that we looked at EMTP-RV. This particular software does have internal components that are designed for studying CT saturation, and they also have protective relays. So The first thing you're going to do is watch the webinar that they've produced for evaluating CT saturation and transformer differential relays. One additional step that you're going to have to do after you've done your ETAP model is you need to digitize the CT excitation curve in order to put that into the program. Once you have that in the program, then the performing of the calculations is not that difficult. And after that, you can also model using EMTP-RV the protective relays within their program. Now, this is a more complicated piece of software, and it does take a little bit more time to set up and to make sure that the results of this program jive with the results you're seeing in ETAP. Specifically, you want to check to make sure that your fault currents all match and the load flow scenarios match so that your two models are calibrated. The additional time it takes to set that type of thing up and calibrate the two models, as well as input the new CT data, you're probably going to take about 60 minutes to do this calculation compared to the easy calculation we just did in ETAP. Now, the cons, of course, for this type of program is that you're going to have to learn a new software, and the software does have a cost. There is a demo version of it, but in order to access some of the features, you need to pay the additional cost. And the cost of this program is equivalent roughly to the cost of ETAP in itself. The other thing that we noted, if you're going to use this program to calculate CT saturation, is you need to modify the standard burden input to their CT in order to get it to match what you need for lead resistance. So let's take a look at the results after you've done that calculation. So for this CT under the higher fault current scenario, you can see we still are modeling a good amount of saturation in this model. You can see that it is calculated in the black line here, the saturated current, and the RMS current is the green. In this case, it shows we're a little bit further above the trip set point than in ETAP. The results are pretty close. They're not exactly the same, but that would be expected. So from here, we say that this CT is probably going to be suitable for this application. We don't think it's going to drop out of pickup, and we don't think that it is going to cause a protective relay issue for us. So end result is this is pretty similar to ETAP, not exactly the same, but it's within the realm of being okay. Now, we can add a protective relay and connect it to the current transformer right here in EMTP-RV. The additional things that will get you is you can check your protective settings. You can set up harmonic restraint settings and things like that to really model the operation of those protective relays. The downside is that you need to purchase an additional module of EMTP-RV in order to study that phenomenon. The next software that we have used to verify is a alternate transient program, ATP-EMTP. This program is a freeware that a lot of people use for modeling transients in electrical systems. This program is extremely complicated, and it really has unlimited aspects that you can model in your system. Lots of people are using this to model various things from lightning strikes to transformer energization, CT saturation. You can pretty much model anything, but you have to boil your electrical system down into individual components, and it's going to take quite a bit of time in order to do that. In order for us to study the current transformer saturation aspect of this, Schweitzer Engineering Lab SEL has developed a paper for how you would model CTs and their saturation characteristics using ATP. In this case, we still have to digitize the CT excitation curve, and we're going to put in all of our wiring and relay data, and then we can perform the calculations using this software. If you want to go further into detail, modeling your various protective relays that are part of ATP draw, you're going to need to learn a different programming language that develops that model. But you can, in fact, then check all of your protective relay settings and harmonic restraints and things like that. This is a very complex software to use, and it's going to take a lot more time. So in our case, compared to the ETAP demonstration that we just did, which took a few minutes to determine if there's a problem, you can spend hours, if not days, trying to configure the ATP system to match the EMTP results. So there is a need to create a new model, and that is going to take some time, and it's very easy once you've created this model to go way overboard and spend more time evaluating items within the model than you otherwise would have spent using ETAP. But let's look at the results from the ATP simulation. So here are the results. Essentially, it's very, very similar to the EMTP-RV results, which you would hope and expect, which is pretty similar to the ETAP results as well. We do show that we have quite a bit of saturation, but the RMS current is still above our tripping threshold by a good amount. So we think that this relay is not going to suffer problems from current transformer saturation. Now, it is possible, of course, to develop your own protective relays. You have to learn this new programming language to set up the input filters and the harmonic restraints. You have to create your own current transformers with saturation characteristics as described in the SEL paper. It's quite a bit of effort, and you can end up kind of going down a digital rabbit hole of trying to fine tune this model, and it ends up taking a significant amount of time in order to set this up, especially if this is your first time. So what does all that mean? I think what it means is that a single topic can spur a big significant effort depending on which type of software you're using. So what can we take away from this? And I would like to think the thing we can take away from this is that we should use a stepwise process for evaluating current transformers. So when we go in to look at a particular system, we want to start that process by using the ETAP calculation method, because that is going to be the quickest and easiest way to determine whether or not you have a saturation problem with your CT selection. You can make a first pass of your calculation using ETAP and then determine if you're right on the edge of having problems with CT saturation in your protective relays. Then you can decide whether or not you want to go into a deeper dive using an EMTP type program. Unfortunately, once you decide you have to go into these deeper dives, there's a significant added cost, potentially either an additional software cost or additional time in learning new programs or developing new models using an ATP, for instance. So one thing I did want to point out is this is just one aspect of the CT selection. Saturation is a topic that's kind of fun to study, and it's kind of interesting the impact of the CTs has on the protective relays. But there are other factors that you need to be cognizant of when you're selecting a CT, such as the input rating on the protective relay. Protective relays can only handle such a high current. So if you have a very low ratio CT, sometimes you can exceed the input rating of the protective relay. So I think at the end of the day, you want to start with a piecewise approach, take a look at your CTs, do your intermittent or your intermediate calculations with ETAP, and then fine tune all your sizing to make sure it's properly sized for the protective relay that you're applying. Thank you.